Okay, so we just have a few problems from the final exam review. First one is number 32, where we're given a quadratic function that represents the daily cost to manufacture a certain type of golf club. So notice it's c of x equal to this quadratic function. Okay. It has a positive leading coefficient, so without being too specific, we know it is a parabola opens up. So clearly this one will have a minimum, which is exactly what A and B are asking for. So we're looking for the minimum cost, or how many clubs should be made to minimize costs. We're just looking for the vertex. So it'll have an X and a C. X is the how many clubs, and C is the cost. Okay. So there's two ways to find, remember, the vertex. We can use our vertex formula, which remember gives you the x coordinate of the vertex, negative b over 2a. Okay, so our b is coefficient of x, so it's negative. Coefficient of x is negative 620 over 2 times a, which is 5. Okay. So we get 620 over 10, or 62. So remember, for part A, that would be 62 clubs. X is your input, and that's the type of the number of golf clubs. Okay. B, then, for minimum cost, we would just have to evaluate that function at 62. So if you plug in 62, you'll get $780. Okay. Remember, an alternate way to find the vertex is to complete the square. Again, this is more standard form for the quadratic. If you want to complete the square, then you can see the shift and see where the vertex has moved. So just as an alternate method, we're going to complete this square. Okay. So remember, we factor out the leading coefficient, 5. So that's x squared. Take 620 divided by 5, that's minus 124x. Not going to worry about the 20,000, remember. So nothing has happened yet. Now we're ready to complete the square. So remember, you take the negative 124, cut it in half, it's negative 62, square it, you get 3844. That's the number that will complete the square. So we put that here. Again, be careful, because you wrote 3844, but you wrote it inside of parentheses. That's being multiplied by 5. So really what you did was put in a 5 times 3844, which is 1920. So we'll subtract the 19220. Okay. So again, 5 times 3844 is that 19220. So subtract it and everything's even. Okay. So we've completed the square. Remember, this is x, should be this one, minus 62, quantity squared, and then we combine those constants. It's 780. So again, in this form, we can see pretty easily the vertex is 62, and then up 780. Remember, this is the number of clubs. This is the cost. So this is part A. This is part B. All right, next one we're going to take a look at is number 38, which is find the real zeros of a cubic. Okay, we can't factor this, so the only way to really get started is to maybe graph it. Keep in mind, if you're going to look at the rational roots theorem, the only possible rational roots, you take the factors of 3, or the constant term, over the factors of the leading coefficient, which is 1. So it's pretty much just plus or minus 3 plus or minus 1 over the 1. Okay, so the only chance we have for these factors would be 3 plus or minus 3 plus or minus 1. Okay, so not too many to choose from if there's going to be a rational function. So we plug in our x cubed minus 8x minus 3. I think I just assume 6. Okay, it's not really easy to see, but if you look at your graph on your calculator, if it's only going to, these are the only possible rational zeros we can have, it would appear that 3 would be 1. I can check on my calculator, so I calculate the value. I just plug in a 3, make sure that's going to work, and it will. Okay, but now I actually divide it out because I have to see what's left over. Okay, so 3 is going to be my root. my coefficients are 1x cubed, remember 0x squared, negative 8x, and negative 3. And we know this should turn out to be remainder 0, so bring down, multiply, always add going down, multiply, add going down, 3 times 1 is 3, and in fact we do get a remainder 0. So at this point we're at f of x equal to x minus 3, and then we've gone down to the quadratic, x squared plus 3x plus 1. Okay. If this factored, we would factor it. It does not, so we'll just use the quadratic formula on that. Okay, so again, we can already see our zeros. We'll have a 3, and then whatever we get by solving this. Okay, so I use the quadratic formula, and the 2 roots from this factor would be the opposite of b, negative 3 plus or minus square root of b squared, which is 9, minus 4ac all over 2a. So that's negative 3 plus or minus the square root of 5 all over 2, which really can't be cleaned up at all. And those are our 3 roots for the degree 3 polynomial. 43, we're asked to divide the polynomial by x minus 3 and figure out what it would be true. Okay, so let's just go ahead and divide it first. So remember, if you're dividing out by x minus 3 in synthetic, really checking if 3 is a 0. So you have 2x cubed, negative 1x squared, remember 0x, and 5. Run through your synthetic, so remember multiply, always add going down. 3 times 5 is 15, add going down, multiply, that's 45. Okay, so our remainder is 50, so it's clearly not a 0, but remember what we do know then is that f of 3, if I plug 3 in, I'm going to get 50. So in your options there, that would be A. All right, 65 was solving some exponential and log equations. Okay, so looking at these, and here's the first 2 are just a couple of exponential. This is a type 1 because 8 and 4 can both be written as a power of 2. Okay, and so 8 is 2 cubed, 4 is 2 squared. Okay, now we have this is a little bit complicated, so let's remember power to a power, we clean it up. So you multiply the exponents, so that's 18 plus 9x. But again, type 1 means both sides are just 2 to a power, so we can equate the exponents. So subtract that 18, divide by 9, and we get negative 16 ninths. Okay. Cannot do that here, right? This is base E. There's no way you could rewrite 4 in base E. Okay. So for type 2, we isolate the exponential, which it is, and then apply our log property. So again, this is base E, so I would use ln on both sides, or just rewrite it. Okay, so you're taking an exponential and rewriting it as a log, so it's log base E, which is ln of 4, should equal to 1 minus 2x. Okay. Subtract the 1, divide by negative 2, and you'll have solved for the x. So ln 4 minus 1 all over negative 2, which maybe cleaned up a little bit better. Multiply top and bottom by negative 1 and get 1 minus ln 4 all over 2. C and D now have some logarithms in there. Okay. So we like to have one log, so here we're going to have to combine these. Okay, but this one already has one log. Okay. So again, we just rewrite it as an exponential. So it's log base 3. The base of the log becomes the base over here. And so we just get the square root of x minus 2 would be 3 squared. Okay. Or x minus 2 equal to 9. Square both sides, and you get x equal to 83. Okay. Here we have to combine the logs. Remember, you need a single log before we can rewrite it. But fortunately, log plus log would be 1 log multiplied. That's your log property. Now remember, when we use these log properties, we're going to have to check. Okay. But now the base of the log becomes the base over here. So we square this out, or FOIL it out. X squared plus 7x plus 12 equals 6. We have a nice quadratic. We can solve that. We'll get 0 on one side. So subtract the 6 over. Fortunately, this does factor. And so for right now, it looks like x can equal 6 or x can equal 1. Okay, we have to be very careful here because we need to check. When you combine the logs, you need to go back and check at least the first step to make sure you're not getting negative logs. So just come over here. So if I plug in, oh, sorry, I think I did something wrong here. Hold on a minute, this should be plus 6, sorry. So when I subtract the 6 over, that's 6. So this is x plus 6, x plus 1. Sorry about that. So I'd be checking these two numbers. So if I check x equal to negative 6, and again, you plug it in the original, it would be log base 6 of x plus 3, or negative 6 plus 3. Or you can already see it's going to be wrong, because I can't take the log of a negative number. This would be trying to take log of negative 3. So x equal to negative 6 is not a solution. If I check x equal to negative 1, again, into the original, I get log base 6 of negative 1 plus 3 plus log base 6 of negative 1 plus 4. Does it equal 1? But again, this is fine. This is log base 6 of 2. This is log base 6 of 3. And you could check what it is. But again, we're taking the log of positive numbers there, so we know we're fine. Okay, so there's only one solution here, x equal to negative 1. And then finally for E, again, we have logs on both sides. We could try to combine them. But it might be a little bit easier since they're on opposite sides instead of moving one to the other side. If both sides are just log, then we can equate what they're taking the log of. So this is just log of 7x minus 12. Well, what do I do about the 2? Well, you can do a log property, and that would be log of x squared. So log of this has to equal log of that. So 7x minus 12 has to equal x squared. It's quadratic, so we're going to get 0 on one side. And we're fortunate here because it does factor to be x minus 4, x minus 3. And so again, we have 2 to check. We did use a log property, so we have to be careful about that. We brought that 2 up as a squared. So if you check x equal to 4, you get log of 7 times 4 minus 12 equals 2 log of 4. But again, this looks like it'll be fine. That's 28 minus 12, which is 16. Here you're also taking the log of a positive number. So again, you can keep checking, but it will work. You just want to make sure you're not trying to take the log of a negative number. And then if you plug in 3, you get log of 7 times 3 minus 12 equals 2 log of 3. Remember, you're plugging into the original. So again, this is 21 minus 12, so that's log of 9 equals 2 log of 3, which is good. Again, logs of positive numbers. All right, last couple here. Number 71. We're looking for, we're told that the half-life is 25 years, so we want the decay rate. So remember, for exponential decay, we have A equals PE, and I'm going to call it, since it's a decay rate, so I'm going to say e to the negative RT. That's the general formula used for decay. We know the half-life. So again, it doesn't matter how much we start with, the initial amount. If I call it 1, the amount at the end of the time would be half that. So e to negative r, and my time is 25 years. Okay, so it's just 1/2 equals e to the negative 25r. This is just e to a power, so can convert to a log. So remember, this is ln, or log base e, so it's ln of 1/2 equals negative 25r. We get ln of 1/2 over negative 25, which is approximately 0.028. So that should be A. And then finally in 72, just a log calculation. You're given a formula here to calculate pH, and you're just told this H3O positive is the concentration which we're given here. So in our case, pH is negative log. You're told this is 1.6 times 10 to the negative 5. So really, you just dump that all in your calculator if you want, and you get about 4.8, which is B.